This video is education purpose only. Myself Dr. Jagdale, Head Department of Chemistry, and today I am going to talk on the topic crystal field theory, short form is CFT. This topic is belong to T.Y.B.Sc Chemistry, semester 3rd syllabus. Next point is applications of crystal field theory in octahedral complexes or complex. You know that in octahedral complex, according to the crystal field theory, metal ion is at the center position and 6 ligands are surrounded by this metal ion. Here ligand number 1, 2, 3, 4, 5 and 6. You know that ligands are electron pair donor and negative end means delta negative is attracted towards the central metal, that is a positive, and there is an interaction between positively charged and negatively charged. That interaction is known as electrostatic force of interaction. And according to the CFT, you know that 100% ionic bonding is formed. The bond form is 100% ionic or purely ionic bond is formed. Here example for octahedral complex is suppose there is formation of here Cr H2O6 3 plus complex ion. Example is Cr H2O6 3 plus complex ion. In this complex ion, chromium metal ion is at the center position and charge on chromium is 3 plus. Here charge is equal to 3 plus. 6 ligands are surrounded by that central metal ion. 6 H2 molecules, they behave as ligand. You know that water molecule is English V shape. And there is a formation of delta positive and delta negative charges. And this delta negative charge is attracted towards the metal plus ion. And there is a formation of 100% ionic bond. Means covalent bond formation concept is not considered in CFT, means crystal field theory, but a bond form is very pure bond and that bond is ionic bond and 100% ionic bonding is occur there. And this is the example for octahedral complex. Here central metal ion is chromium 3 plus. 6 ligands are surrounded by that and charge on complex is equal to 3 plus. You know that chromium has atomic number 24. And if you see the applications of CFT in crystal field theory, here central metal ion is chromium. Chromium has atomic number 24 and ground state electronic configuration is here 1s2, 2s2, 2p6, then 3s2, then 3p6, then 3d5, then 4s1 and 4p0. And you know that in chromium and copper there is an exception in electronic configuration in d orbital. In place of 4 electron in 3d orbital, there are 5 electrons in 3d orbital, and in place of 2 electron in 4s orbital, there is only 1 electron, that is 4s1, and 4p orbital is empty. In this complex ion, charge on chromium is plus 3. How plus 3 is formed? There is a removal of 3 electrons, means 3 electrons from that outermost 4s orbital and 3d5, and in chromium 3 plus complex, here charge on Cr3 plus is equal to 1s2, 2s2, 2p6, 3s2, 3p6, and here 3d3, 4s0 and 4p0, and 3 electrons are removed from the valence shell from the 4s orbital and 3d. When 3 electrons are removed, then electronic configuration is 3d3, 4s0 and 4p0. And in 3d orbital there are 3 electrons only. Then if you plot or draw the energy splitting diagram for this octahedral complex, you know that it is represented as, here is energy. Then suppose that chromium 3 plus is at a free state and these are the 5d orbitals, 1, 2, 3, 4 and 5, and this is for the free ion. Free ion means Cr3 plus ion. In 3d orbital there are 3 electrons and these 3 electrons are represented like this. These are the 3 electrons. When 6 H2 ligands approach to the central metal ion Cr3 plus, hypothetically there is increase in energy and that energy increase is shown like this, and again these 5d orbitals are represented like this. Here again 3 electrons are there. Then when 100% ionic bond is formed, the degeneracy of these 5d electrons break into 2 sets. One is known as Eg set and second is known as T2G set, and it is represented here. This is Eg and these are the 3d orbitals known as T2G. You know that 5d orbitals are dxy, dxz, dyz, dx square minus y square and dz square, and these 5d orbitals split into 2 sets. One is T2G and second is Eg. T2G 3d orbitals are dxy, dxz and dyz. Eg2 orbitals are dx square minus y square and dz square, and this is average energy level. It is represented as AE. It is represented as AE, means average energy. The distance between T2G and Eg is represented as 10 dq. For octahedral complex, it may be represented as delta O, and this is the representation for octahedral complex. Short form is OH. This is the first step. This is the first step, and in first step, hypothetical energy is increases from free ion to the hypothetical, means energy is increased, but all 5d orbitals are again in the same energy level. Same energy level means degenerate, and the energy of 5d orbital is same. And for chromium 3 plus, these are the 3 electrons and they are unpaired electrons. Then from T2G level to the Eg level, this distance is represented by minus 4 dq, and from average energy to the Eg, the distance is plus 6 dq, and total is equal to 10 dq. Total is equal to 10 dq. Here T2G in octahedral field or octahedral arrangements. In second step, T2G has lower energy as compared to the Eg orbital because energy is represented, and in this direction there is increase in energy. And what? T2G has lower energy as compared to the Eg orbital. What are T2G orbital? There are 3 T2G orbital. One is dxy, second is dxz, and third is dyz. What are the Eg orbital? There are 2 Eg orbital. One is dx square minus y square and second is dz square. The energy difference between T2G and Eg is represented by 10 dq. And this middle dot line indicates that average energy. From average energy to T2G distance is minus 4 dq, and from average energy to Eg distance is equal to minus plus 6 dq. And this is the splitting of octahedral field, means 5 degenerate orbitals split into two sets. One is T2G and second is EG, and T2G has lower energy as compared to the EG. If you represent these 3 electrons in that splitting diagram, one electron is here and it is represented as single electron here, then second single electron here, and third single electron here. And for filling the electrons in crystal field energy level diagram, there are some rules. First rule is electrons goes to the lower energy. You know that T2G has lower energy as compared to the EG orbitals. Therefore, these electrons goes to the lower energy. Second rule is that filling of this electron take place according to the Hund's rule of maximum multiplicity. And you know that Hund's rule of maximum multiplicity is pairing of electron will not start till there is a single electron in each orbital. You know that this orbital is dxy, this is dxz, and this is dyz. First of all, single filling take place, and after that there is a pairing of electrons started. Then promotion of electron take place on the basis of distance from T2G to the EG orbital. When the distance is more, you know that complex is known as strong field complex, and when distance is less, then that complex is known as weak field complex. In weak field complex, that electrons when increase, then that electrons are easily promoted to the excited state, means higher energy level, and then there is a pairing started. When strong field is there, in place of going electron to the EG orbital, means higher energy, electrons start pairing here. And in that application in octahedral field, from this energy level diagram, means splitting diagram for crystal field, you can find out the number of unpaired electrons, means magnetic property or magnetic moment. Means next point is how magnetic moment is determined by crystal field theory, and magnetic moment is determined by using spin only formula. Spin only formula, mu effective is equal to under root of n into n plus 2. N into n plus 2. Mu effective is magnetic moment. Then n is equal to number of unpaired electrons. You know that diamagnetic means all electrons are paired. Paramagnetic means presence of unpaired electron. And here n indicates number of unpaired electrons. N indicates number of unpaired electrons. You know that when n is equal to 1, that value is equal to 1.73 bm. Bm is Bohr magneton. Unit for magnetic moment is Bohr magneton. When n is equal to 1, when you put that value in this equation, n is equal to 1 multiplied by into the bracket n plus 2 is equal to 3. Under root of 3 is equal to 1.73. Under root of 3 is equal to 1.73 bm, and for n is equal to 1, in this complex ion CrH2O6 3+, there are 3 unpaired electrons. There are 3 unpaired electrons, means n is equal to 3. When that value is equal to 3, here 3 multiplied by into the bracket 3 plus 2 is equal to 5. 5 3s are 15. Under root of 15 is equal to what? 3.88 bm, and that value is observed for CrH2O6 3+ complex ion. Like that, you can calculate the magnetic moment for different substances having different d systems, means d1 electrons, d2 electrons, D3 electrons, D4 electrons, D5 electrons, D6 electrons, D7 electrons, D8 electrons, D9 electrons, etc. Means various systems are there. These systems are determined from the charges on metal ion. These systems are determined from charges on metal ion. In this complex ion CrH2O6 3 plus, charge on chromium is equal to 3 plus. Ground state electronic configuration is 3d5 4s1. In Cr3 plus 3d3 means system is D3. For D3, number of unpaired electrons is equal to 3. Spin only formula mu effective is equal to under root of n into n plus 2. Here n is equal to 3. By putting that value, we get that value is equal to here 3.88 bm. And observed value and calculated values are quite near to each other, that indicate here in CrH2O6 3 plus complex ion 3 unpaired electrons are there. That complex ion is paramagnetic in nature because 3 unpaired electrons are there, and these unpaired electrons are represented here and they are remain in the T2G orbitals. And all these electrons are unpaired because according to the Hund's rule of maximum multiplicity, pairing of electron will be not started till there is a single filling of electron in each orbital. Here single filling, single filling, single filling, these 3 electrons are there. Like that, you can calculate in various octahedral complexes, and actually there are 2 types of splitting occur in octahedral complex. One is known as strong field and second is known as weak field. One is known as strong field and second is known as weak field. In strong field complexes, that 10 dq is more, and in weak field complex that 10 dq value is less. And that strong field and weak field in octahedral complexes depend upon the spectrochemical series. In spectrochemical series, there is arrangement of ligands on the basis of strong field and weak field. Here, suppose there is a cyanide minus ligand, Cn minus. Here, splitting is higher as compared to the nitrate ligand, that is NO2 minus. It has a higher energy as compared to the orthophenol. It has a higher energy as compared to the ethylene diamine. It has a higher energy as compared to the water molecule. H2 has a higher energy as compared to the OH minus, has a higher energy here. Fluoride minus, chloride minus, then bromide minus and iodide minus, and that series is known as a spectrochemical series. In spectrochemical series, position of cyanide ion is first and halides are at the end. That indicate cyanide forms the strong field complexes and halides forms the weak field complexes. Suppose there is a formation of here Fe, then Cn6 3 minus complex ion. That complex ion is strong field complex, means in that complex ion that 10 dq value is more. Arrangement is same because it is octahedral complex. And second complex ion is, suppose there is a formation of Fe F6 3 minus. They belong, this complex belong to the fluoride. You know halides are fluorine, chloride F minus, chloride Cl minus, Br minus and I minus. This is a weak field complex. Weak field means this distance is less, and strong field means this distance is more. What distance here? 10 dq value in between T to G and EG. Here below the average, there is minus 4 dq. Above the average, there is plus 4 dq. But Fe-CN6-3- is strong field complex and Fe-F6-3- is weak field complex. In this complex, central metal ion is Fe3+. In second again, central metal ion is Fe3+. But 6 cyanide ligands are directly attached to the what? Central metal ion, and here 6 fluoride ligands are directly attached. Here cyanide is a strong field ligand and fluoride is weak field ligand. And if you consider their atomic number etc., you know that iron has atomic number 26. In the ground state, electronic configuration is represented as 3d6, 4s2 and 4p0. Charge on iron is 3+, therefore 3 electrons are removed and here is a 3d5. Here is 3d5. And filling of that 5 electron take place here. 1, 2, 3, 4, 5. 1, 2, 3, 4 and 5. That is weak field. And for strong field, 1, 2, 3, 4, 5. 1, 2, 3, 4. Here pairing start. 4th electron go here. 5th electron go here. Means in strong pair, there is only one unpaired electron and n is equal to 1. And in this Fe-F6-3- weak field complex compound, there n is equal to 5 because 5 unpaired electrons are there. By putting these values in mu effective, that is equal to under root of n into n plus 2. When n is equal to 1, that value is equal to 1.73 bm, and when n is equal to 5, that value is equal to here 5.92 bm, that is Bohr magneton. And if you prepare these complexes and measure their magnetic moment, these values are quite near to 1.73 bm for first complex, that is Fe-CN6-3-, and for second complex it is 5.90 bm. It is near to the 5.92 bm, and that proves that this first complex is strong field complex and second is weak field complex. Okay, we'll stop here.